All right. Oops, I need to be able to see that stuff down there. Okay. Settings. Video is good. Audio. There we go. That. Okay. All right, we've got 3 on Zoom. There's Lydia. There's Tyler. And there's Julianne. Okay. With you 3 and 1 in the class, that's 4.
I'm on my way to class. I'm just kind of stuck in traffic.
Say again?
I'm on my way to class. I'm just stuck in traffic.
Oh, I see. Okay. Let's see. Let's get things in focus here. Back it up some. Yeah, it's probably about as good as we're going to get and keep the board. I could move it over a little bit like that. And then, is that still on? Oh, I can go even further. There we go. I guess most everything in line. This one out of the way. and that turn on. Go. Here we go. 2 in class and 3 on Zoom. Oh, yeah, 3 on Zoom. One was me.
Are we going to lab again?
We'll see. Let me check the schedule and see what would happen if we had to postpone it.
She's not in mine, right?
Right.
You still in class?
Yeah.
That's what we're calling it.
So the lab would be if we push the lab till next week, then the last lab will be the week after that, right after that. May 1st. What are we doing May 1st? May 1st is a regular day, isn't it? Okay, we can push all right, I pushed both of them. And that would still give you a week in between. All right, let's see if anybody else shows up. Okay. We'll try to get through this chapter. And I need to put some identifying marks up here. Spring 2019. This is chapter 8. Yep. Chapter 8. CHEM6. Chapter 8.
So do we have one more chapter after this one?
Mm-hmm. Yeah, chapter 9, and then we're done. And this is bonding. On I think 10. There we go. Now, let's see what we can learn about bonding. These are general concepts of bonding. And they're more or less taken in historical order. Because our early concepts were pretty raw. And we, as with most theories, they answered some questions, but they didn't answer every question. And eventually, the concepts of bonding had to be restricted in their application. And then we moved to another level, which would encompass those areas that were not well described by earlier theories. Okay, first question is, what do we mean by a chemical bond? And along with that, why do atoms bond with each other to form compounds? Why don't they just stay by themselves?
For energy.
I'm sorry?
Is it the form of energy?
Energy has a lot to do with it. Yes, indeed. And then how do atoms bond with each other to form compounds? Those are the questions we're going to focus on. The chemical bond, the nature of the chemical bond was kind of an open field for quite some time. And the first really concerted effort and successful effort in describing the chemical bond came from Linus Pauling, who was a biochemist, I think he was. But he pulled everything together that he could find on the chemical bond, his understanding, and made some coherent description of what a chemical bond was and why compounds form. And he did such a good job of it, he got a Nobel Prize for it. One way to describe a chemical bond is it is a force. And it's the force that holds atoms together. you can describe it in terms of the bond between two atoms or the collection of bonds that hold a molecule together. And in fact, eventually we're going to get to the place, that's in the next chapter, where the concept of bonding applied across an entire molecule is the way to go. It gives you a more complete description of what's happening when compounds are formed. But we're going to take baby steps first. In general, and here comes the energy part, a bond will form if the bond of the aggregate together, if the energy of the aggregate together is less than the combined energy of the parts before they bond. So it's always trending toward the lower energy level. That's the driving force for the formation of a bond. Now, having said that, bonds can form in such a way as the product overall has more energy than the reactants. A perfect example is the formation of nitroglycerin. Nitroglycerin's got a hell of a lot more energy than nitric acid and glycerin together. But the stability of the compound depends on a local minimum. Right? So you have to be more specific about before and after. Of course, it's not very stable. I mean, all you have to do is just look at it cross-eyed and it'll blow up in your face. Okay, so here's a representation of two hydrogen atoms independently and coming together to form an H2 molecule. Now, room temperature and 1 atmosphere pressure, H2 is the preferred form of hydrogen. You won't find individual hydrogen atoms. So this is a laboratory experiment, or in this case, a thought experiment, where we have two independent hydrogen atoms coming together to form a bond. And the nuclei, represented by these plus signs, which is one proton, they only get so close together, and then they don't get any closer. They get just close enough so that their electrons can mingle. And that is, in effect, the bond. Because when atoms approach one another, what do they see first? They see their electrons. And so that's where the bond forms, with the electrons. This is another way to look at it. So on this axis, we have the potential energy of the separate atoms or for the compound. And this is the distance between their nuclei. Right? So this is, it's better to use this graph in reverse. In other words, start out here, where they're separate, and then follow this line along where they get closer and closer and closer. And the energy drops as they get closer, and there's an ideal distance between them, the bond length. And it's different for different elements, right? This just happens to be for the dihydrogen molecule. So at this point, you have the strongest bond at the lowest potential energy. If you try to push them closer, then you're adding more energy and weakening the bond. Right? And the main reason for that is proton repulsion. You try to push the nuclei close together and they don't want to go there. That's why fusion reactions have to be, at present, have to be accomplished at very high pressures and very high temperatures. You got to move those nuclei close enough to where they will fuse. And we could have a 2 or 3 hour discussion about the strong nuclear force and the weak nuclear force and all that. But we're not going to do that. We're talking about chemistry here, not nuclear physics. Do you need a copy of anything? Probably do, don't you?
Probably. I have a question. So you know attendance is 11% of your grade?
What? Say it again?
Your attendance is the 11% here?
Yeah.
So does that go in there after, like, you counted your attendance for the whole semester?
No, it goes in simultaneously. Each time I update your attendance in my spreadsheet, it calculates it in. Yeah. Let's see. I think I also, yeah, I'll leave that one. This one. There you go.
Yeah, I stop at the meeting and go get blood drawn stuff.
Okay.
Yeah.
You're here.
I would have been later if I waited around for coffee. So I told him, I'll see you next time.
Okay. So we can subdivide bonding into two basic types. Now these are for our benefit. In actual fact, bonding is on a continuum from extremely ionic to almost purely covalent. And what I mean by that is the electrons for ionic bonding have been transferred completely from one atom to the next. And then the attraction is purely electrostatic, like sodium chloride salt. Whereas covalent bonding is a sharing of electrons. And that's what we saw with the dihydrogen molecule. The electrons were shared between the two hydrogens to form the bond. All other bonds are somewhere in between ionic and covalent. They always have some ionic character and some covalent character. If you have this sharing, for instance, with, you have one electron from that hydrogen and one electron from the other hydrogen. Okay. So this is a single bond, and a single bond, a bond, always represents two electrons. So in this case, they're sharing electrons. And since they're the same atom, they both pull on the electrons with equal strength. And this is a purely nonpolar covalent bond. Okay? If you have two different elements in a covalent bond, like hydrogen and fluorine, then the fluorine pulls on electrons more strongly than hydrogen, and that shifts electron density more toward the fluorine than the hydrogen. In that case, you have a polar covalent bond. Okay? Let's see, do I have negative, right?
Yes.
Okay. Here we go. You have copies of all the papers there, don't you?
For this upcoming test and stuff?
For chapter 8.
Yes.
And we represent the, for the nonpolar covalent bond, we have no representation for the distribution of electrons. But for the covalents, we draw an arrow showing the direction that the electrons prefer to go, and that gives you the plus end of the arrow. Okay. So this is called a, this arrow represents a dipole. It's like, think of a magnet, has a north and a south pole. This has a negative and a positive pole. And this difference in electron distribution can be measured. You just need a sophisticated instrument with plates, one charged negative and one charged positive, and you can measure the strength of the charge distribution between those two plates and relate that to the polarity of the bond. Okay, so a chemical bond, let's recap, can be described as the force that holds atoms together so that they function as a unit. when atoms bond, they form molecules if the energy of the aggregate is lower than the energy of the separate atoms, with some qualifications. But that's a general statement that is useful. So how do they bond to each other? Well, they either completely transfer their electrons to form ionic bonds, like sodium will be like that, chlorine like that, and if you transfer an electron from here to here, then chlorine becomes negative, sodium becomes positive, and you get an attraction between them based on electrostatics. Or you can share electrons, as we did with dihydrogen, and you get a covalent bond. In that case, a nonpolar covalent bond. Now, I mentioned the unequal attraction of electrons. That can also be quantified. It's a term called electronegativity, which means the larger the number, and the numbers are always positive, the larger the number, the more strongly the element attracts electrons to itself. This is a calculation for it, but I'm not going to have you do any of those calculations. You just need to understand how to use the values. Linus Pauling, I mentioned him earlier. He came up with a system. There are several systems available for describing electronegativity, but Pauling is generally accepted. The strongest attraction for electrons, I'll give you a periodic table here. The strongest attraction is up here. Fluorine has the very strongest attraction for electrons of all the elements, and it's given a number of 4.0. The weakest attraction is down here at about 0.7. So the range is 0.7 to 4. So that's useful because if we subtract those values, say we have a value here and a value here, and you subtract them and find out what the difference is, then the larger the number, the more polar the bond, which means the greater the difference between the electronegativities, the greater the polarity of the bond. Let's see. Trends. Right? We talked about trends before. Ionization energy, right? From lower left to upper right, increases. Electron affinity, we talked about, didn't we? Right. From lower left to upper right. Atomic radius gets bigger from upper right to lower left. Now we've got another one, electronegativity. It also increases from lower left to upper right. So this is going to be a more electronegative than that one is, than that one is, than that one is, than that one is. And from left to right, the electronegativity is going to increase in that direction. Now, within a period, the attraction for electrons increases from left to right because you're adding protons. And you're not adding energy levels that could shield those protons. So the effective nuclear charge increases from left to right, and that adds to the attraction for electrons as you add protons. You increase electronegativity from bottom to top because you're changing energy levels. And as you add electrons in these upper energy levels, you're shielding the protons that have been added on the inside. So you're actually decreasing the effective nuclear charge as you go from top to bottom. So conversely, as you go from bottom to top, you're increasing the effective nuclear charge. And fluorine is the strongest attractor of electrons in the periodic table. So there's a graphical representation. In general, we increase from here over here like that. But you'll notice some discontinuities in here. Like we increase across here, and then we drop down as we get to the farthest reaches of the transition metals. We drop down here. One of the reasons for that is the d orbital is full. It's happy. It doesn't want any more electrons. But once you start back up into the p orbitals, then you get that additional nuclear charge that is not being shielded any longer in terms of electron stability. I see a dip right here too. So remember when I was talking about the electron configurations, and when you get to chromium, rather than bringing a D4 electrons, it's a D5, and it steals one from the s orbital. Right? But here you have completely filled, a half-filled d orbitals, and that adds to its stability, so it doesn't attract electrons as strongly because there's no place for them to go. Not without adding energy. And then over here, similarly. So we get this little dip in here, and we get this little dip in here, simply due to the stability of the half-filled or the full-filled d orbitals. So let's see if we can use what we've learned to answer these questions. Which has more attraction for an electron, lithium or fluorine? Well, you look at the periodic table. Here we go. Lithium is here. Fluorine is here. We increase electronegativity from left to right, so fluorine should be higher electronegativity than lithium. In a bond between fluorine and iodine, which has more attraction? Well, in that case, you're looking at a group, and this is going to have less attraction than this one does. So fluorine, again, will be the stronger attractor for electrons. There we go. Oh, this is that's just saying the same thing over again. And for the reasons that I gave you. This table comes straight out of your textbook. And what it's meant to describe is what I mentioned earlier, is that every bond has some covalent character and some ionic character. The greater the difference in electronegativity, the more ionic character there is. So if the difference is 0, what do you have? You got two of the same elements bound together, like dihydrogen, or dinitrogen, or dioxygen molecule. So those would be virtually pure covalent, with very little ionic character. And then if the difference is very large here, for instance, well, lithium and fluorine, they're widely separated, and they're going to be predominantly ionic in character. So let's see if we can range these in from most to least polar. So the most polar, and remember, if the bonds are going to be polar, there has to be a large difference, separation on the periodic table. So let's see, which are the closest together? Oxygen and fluorine is the closest, so that should be the minimum. That would be the least. And the farthest apart should be carbon and fluorine. Right? So this would be the most, and then nitrogen and fluorine would be in the middle. Okay, oops. I gave away the secret. That one was fairly simple because we had the same fluorine attached to each one. In this one, we've got different. We've got carbon and fluorine, right? So it's very widely separated. We have nitrogen and oxygen, which are right together, so that should be minimum. And then silicon and fluorine, which is actually more separated than carbon and fluorine, so it should be the greatest. And the least should be nitrogen and oxygen. So there's silicon and fluorine, then carbon and fluorine, then nitrogen and oxygen, in that order. How about this one? Well, chlorine and chlorine is going to be nonpolar, so that's your minimum. Boron and chlorine are very far apart, and sulfur and chlorine are very close together. So this one should be the minimum, then this one, then that one. Okay? As a general trend. The only way to be absolutely certain is to get the electronegativities, subtract them, and find out. That will quantify your arrangements. Let me see. How are we doing on time? All right, let's see. I'm going to have to skip some stuff to be sure we get all this covered. So we're going to skip that one and that one. So the dipole moment is represented by that arrow with a plus sign on one end of it. And if you have, say, for example, carbon tetrachloride. Now, what do I mean by that? That means the chlorine is back behind the board. Okay. So arranged like that, it forms a regular tetrahedron. Okay. Carbon and chlorine are sufficiently different so that you're going to have polar bonds there. So we represent the bonds like this. Each one of them is polar toward the chlorine. But when we add them all up, what effect does that have on the whole molecule? Well, they're all pointing to the apexes of a regular tetrahedron with the same dipole moment. They all cancel one another out. So the bonds are polar. The molecule is nonpolar. So what does that tell us? That tells you need to know two things about a molecule to tell whether it's polar or nonpolar. First, the individual bonds. Then its geometry. What shape is it? An example of one where water, right, and it happens to have some lone pairs up there. So the water molecule is bent, and the polarity of the bonds are like this, right? Plus those negatives up here. So that means that when you add these polar bonds together, you get a vector sum that gives the water molecule its polarity. So the bonds are polar and the molecule is polar because of its shape. And we give it a, since these are slightly positive, we use the Greek delta to show us that there is a shift of electron density toward the oxygen. It's not a complete, it's not an ionic shift. Electrons haven't been completely transferred. But there is a significant amount, and that gives this side of the molecule toward the hydrogens slightly positive and toward the oxygen slightly negative. Carbon dioxide is a different example. Actually, that. So each of these bonds is 2 electrons. So we have 2 there, 2 there. It's a double bond there. Polarity is toward the oxygen. But they cancel one another out because it's a linear molecule. That means carbon dioxide is nonpolar. That explains the difference between the freezing point of water, 0 degrees centigrade, and the freezing point of carbon dioxide is minus 78.5 degrees centigrade. That's dry ice, and this is water ice. The polarity of the molecule gives you a stronger attraction among the water molecules, means that it takes it melts at a higher temperature. You have to add more energy to get the molecules of the solid to break apart and make a liquid. Whereas with carbon dioxide, the attraction is less strong because it's nonpolar. And that means that at a lower temperature, you can change it from solid to actually gas. Okay. Let's see. These are regular shapes. If you have a, here's your carbon dioxide, right? So that's carbon and that's 2 oxygens. And it's linear. If you have 3 with a polar, 3 molecules around the central atom, that gives you a flat planar triangle. We call it trigonal planar. And if you have 4, like carbon tetrachloride, around the central atom, that's a tetrahedron. Okay. Now here's another way to think of why bonds form. We've talked about the energy, but this is a useful concept also. It's the formation of the octet. It doesn't always work, and it works best for the elements with s orbitals filling and p orbitals filling. That is the first 2 columns and the last 6. But when you get into the transition metals, then it doesn't work as well because you're dealing with d orbitals. Octet is dealing with s, and p, right? So you can have 2 here and 6 there maximum. That's where we get the octet. 6 electrons from the p, 2 from the s, equals 8 electrons, or the octet. And atoms that bond with one another, particularly those in the 2nd and 3rd, and some in the 4th period, prefer to form an octet. That is, if they can take electrons and make an octet, or give up electrons and satisfy an octet, then that is a driving force for reaction. For instance, let's say we want to form a compound with oxygen. And we want to react that with potassium. Okay? Oxygen already has S2 and P4. So it needs 2 electrons to make an octet. Right? We need to add 2 electrons here. Potassium has an S1. So rather than add 7 electrons, which would be difficult, we just remove that one S, which is in the 2, 3, 4. That's 4S. But there's also 3p6. So if we remove this electron, then it has an octet. by that removal. Whereas with this one, we add one, and that makes it the octet, which would be in the 2. Okay? By doing this, we completely transfer these electrons over here. So this potassium and oxygen will form an ionic compound by that transfer. It doesn't have to be that way. For instance, if we just take 2 oxygen atoms, okay, and we have S2P6 and S2P6, then all we have to do is share 4 electrons. 2 electrons from here, 2 electrons from here, shared. Now this one thinks it has those 2 electrons, which makes it an octet. And this one thinks it has 2 electrons from here. It thinks it has an octet. Now mathematically it doesn't, right? But sharing makes it think it has an octet, which means it looks like neon. Okay? So the trend toward having an octet is the tendency for elements to want to look like, electronically speaking, to look like noble gases. Now let's see. I don't want to jump too far ahead. Wait a minute, we did Lewis structures already, didn't we? Did we not do Lewis? Lewis dot structures? We didn't do Lewis. Okay. Well, let's hold on those. There are exceptions to the rule, the octet rule, and they usually are transition metals or elements that have access to d orbitals. Right? So as you move down in the periodic table, you start encountering d orbitals, and that makes other electrons available for transfers. And then the octet rule kind of falls apart. So these are for, ideally, it works best for periods 2 and 3, the octet rule. Those are some other examples. All right, so when do ionic compounds form? With which elements? Well, usually with metals and nonmetals. And the farther apart they are on the periodic table, the more likely they are to form ionic compounds. If you have 2 nonmetals together, you can be assured that their bonding is going to be covalent, such as 2 oxygens, or a nitrogen, 2 nitrogens and 4 oxygens. They're both nonmetals. Those are going to be sharing electrons. So what's an isoelectronic series? Well, iso is the Greek prefix that means same. So all that means is each one of these in this series, and this is not the only isoelectronic series, this is just an example. Each of the ions or elements in this series have this exact same electronic structure. Right? So oxygen, 2 minus, starts out with 8 electrons, and that would be 1s2, 2s2, 2p4. But we're going to add 2 electrons, right? So that means we're actually 2p6. Okay? Fluorine has 9, but it's got 1 extra. So it starts out like this, like that, and like that. But we add an electron, give it the same electronic structure. And we can do that for each one of these. Either by adding electrons or subtracting electrons gives us that electronic configuration. They're all isoelectronic with one another. That's all that means. Okay, we're going to have to skip those. There's not enough time. Okay, short discussion of lattice energy. What does lattice energy mean? Lattice energy refers to ionic solids, right? So, I do have a couple for you. I'll let you sign in. Where was the traffic?
Getting on the interstate at Princeton.
Oh.
Somebody wrecked coming onto the on-ramp.
Oh, okay. Well, that's different.
I got stuff with rugby.
Usually it's construction. Okay, so lattice energy refers only to ionic solids, like those little cubes of sodium chloride. You know, what holds them together. This is an expression of how much energy is released when, I'm going to use sodium chloride as an example. Sodium, positive ion in the gaseous state, and then chlorine, negative ion in the gaseous state, yield sodium chloride solid. So we're going from gaseous ions to a solid, and there's energy released. So this is exothermic. In fact, it's very exothermic. Gives up a lot of energy when these ions come together to form that solid. And this is just an explanation of what that energy, lattice energy represents. It depends on the charges of each of the ions. So there's like the charge of sodium and there's the charge of chlorine. And here's the distance between them, right? So that's like the bond, the distance between the bond distance, right? And it's similar to Newton's law of universal gravitation. It depends on how big the planet is and how far apart they are as the strength of the attraction. So this is the arrangement. Gas ion, gas cation, gas anion yield neutral solid. Then the energy is the lattice energy for that reaction. Now let's use that to look at the reaction of a metal and a nonmetal. So our metal is going to be an M and our nonmetal is going to be an X. Right? So when we bring those together, they're going to form this. And they're going to have an enthalpy associated with it. Okay? We can look at that as several different steps. So this metal is going to be solid. So what's the first thing that has to happen to that metal? First thing that has to happen is we have to make a gas out of it. Right? That's endothermic. That takes energy. Then we're going to take the gas and we're going to ionize it. That's also endothermic. We have to add energy. Let's scratch that on me. Try a different color. So now we have the ion in gaseous state. Right? So we got that one done. Now we need to take the anion, and what we're saying is that it's probably diatomic. So that means we're talking about probably one of these, or maybe that one. And these typically are a gas to begin with. So all we have to do for this one is break the bond between the two X's. That's also endothermic. Then we have to take this one and add an electron to it. That's exothermic. Because as the electron moves to a lower energy state, we give up energy. Exothermic. Now that we have this one in a gaseous anion and this one in a gaseous cation, then we can put them both together, this one and this one, and the lattice energy is figured in. So in this one we have to add energy, add energy, add energy. We get energy back, and here you get a lot of energy back. Huge amount of energy back. And all of these added together will give you this value. What's the enthalpy of that reaction? Actually, this should be to a gas. So that means, let's see. Actually, that's not right. It should be that. It should be this there. That's right. So what is this? Remember that one? That's the heat of formation for that compound. And that's how it breaks out, each of those steps. And this is what they look like. So you go through each of these endothermics. You get an exothermic here, and you get ionization energy, get these various energy inputs and returns. But then when you get to this point, and they come together, you get this huge amount of lattice energy return. So overall, you start with, let's see, this one. These are two scenarios, this one and this one. And the difference is the same. Well, no, that's not the same. That's a different scenario. This is the one we're interested in right here. So here's the delta H, and this is what had to happen to get you there. It's kind of like Hess's law, right? It's a state function. Doesn't matter how you got there, calculation still gives you the same answer. So you can add equations together. Each one of these has a value to it. Add them together to give you that, to give you this one. Add them all together to give you that one. And you add individual energies together to get you that. So it's another way of using Hess's law. So here's the equation for formation of lithium fluoride. Remember how we write that one? Right? You start with a compound. We did that, didn't we? Heats of formation. Did we not do that? Okay. We need to do that. When you hear or read the phrase enthalpy of formation or heat of formation, this is what we mean. And we're going to use lithium fluoride as an example. You start with the product. Standard temperature and pressure means this is going to be a solid. That's your starting point. heat of formation of that compound. What does it take to get there? Now, after you write that compound and it's correctly balanced in its formula, can't touch it. There's just one of them. On this side, you have to do anything you can under standard temperature and pressure to give you that one. So fluorine, under standard conditions, is going to be a diatomic gas. And lithium is going to be a solid metal. Now you use coefficients, fractions if you have to give you this compound. So we need one fluorine, that means half of that one, and one lithium. So this is the formula of the reaction that will give you the heat of formation for that compound. Okay? And then we can go through the various constructs that I showed you before for that theoretical metal and non-metal reacting. And that's what you end up with. So there's your Hess addition of the equations to give you the final. And then if you add up all these energy changes, you get that delta H formation. All right. I'm not going to spend a lot of time on this one. If there happens to be a review question, it should be self-explanatory. Measuring the percent ionic character. It's just to illustrate that every bond has some ionic character. Strange as it may seem, you have two oxygens together, it does have some ionic character, simply because the electrons never stay put. They're always moving. Let's see. There's an operational definition for ionic compounds. Right? Rather than be theoretical about it, one way to tell if you have an ionic compound is to take the solid and melt it and see if it will conduct an electric charge. Right? It may take a lot of heat to melt the compound, like sodium chloride. It's several hundred degrees. But once you get it in that liquid state, will it conduct electricity? If it will, that means you have individual ions that can move. So you have an ionic compound. If you melt sugar, it still won't conduct a charge, right? There's no ions. So that means sugar is definitely non-ionic. Okay, so now we're going to look at some models. First of all, have I described characteristics of a model yet? Maybe it'd be worth hammering that one again. Let me see how much more we got. We might have to. Yeah, we're going to have to. Because we got to get this chapter out of the way. Oh, we have a buffer day on Monday. All right, so we don't have to finish it today. Right? We just need to find a convenient breaking point. And then we can finish the discussion on Monday. Oh, we are going to talk about Lewis structures. Good, good. So let me go down to I'll just use up the time we have, and then we'll go in the lab. The first condition for a model is to recognize that a model does not equal reality. It's got model airplane, model battleship. Those are obvious. Intuition there is they are not the real thing. Right? Science is the same way. Our models are not reality. They're a representation of reality to try to help us wrap our minds around what's actually going on. Right? Consequently, we have to make some assumptions. We have to say, the model is oversimplified, right? So that leads to some inconsistencies between the model and the real world. But we use models to help us predict what's going to happen. So if we have what we think is a good model, and we make a change in the model and see what happens to it, then we compare that to the real world and see if we get the same result. That's one way to confirm your model. Okay, so global climate models that the IPCC has been using and various researchers have been using to predict the global temperature change in the next 10, 20, 100 years, they all fail. None of them work. So those are bad models. Generally speaking, models become more complicated with age because we add factors to them. We tweak them a little bit to try to help us apply them in under new circumstances. Okay, that's one way to do it. Tweak your model, then it works better. Okay, so when your model fails, what do? One is tweak it. Okay. Change it a little bit, then maybe it'll work better. Second option is restrict it. Restrict application. So you just say, all right, this model will only work under these circumstances. If you go outside these boundaries, it's worthless. Perfect example. Newtonian physics. Newton's models work under restricted parameters. You get outside those parameters, in other words, if your world gets smaller or if it gets huge, Newton doesn't work anymore. If it gets huge, then we use Einstein. Relativity. If it gets really, really, really small, then we use quantum mechanics. All right? That's option one, option two. Option three, if your model fails and you don't want to do either one of these, or you've tried those and you're just dissatisfied, throw it out. Start over. That's what should be done with climate models. Throw them out. Problem is, too many careers and too much money invested, they won't give them up. So it's not science anymore. It's politics and business. Crony capital. Okay. So that's what you do with your model when it fails. One of those three things. Every model has assumptions. That's part of the simplification process. And you have to understand what the assumptions are so that you don't misuse the model. If you ignore the assumptions, then you get into regions where your model is more than likely ineffective, will not work. Now, sometimes we breach those assumptions just to see what would happen. And that's valid, but you have to recognize that if it doesn't work, then the assumptions were correct. And you need to go back and stay within your boundaries. And just because a model is wrong doesn't mean it isn't useful. Right? For instance, the plum pudding model for the atom. Remember where you have protons and electrons just scattered around there like plum pudding. It wasn't right, but it gave us something to reject for something else. It was a competing theory. Okay, so there's what you do with your different models. So what do we mean by bond energy? Bond energy, we focus on a single bond. So we have something here bonded to something there. How much energy does it take to give you individual atoms? That's the bond energy. Now you can look at huge molecules. Let's say, I don't want to get too huge, but let's say we have ethanol. Oops, got a bond here. Okay, that's ethanol, the drinking kind. Bond energies, you would have a bond energy here, 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 and here. And these would all be the same bond energy because the hydrogen is bonded to the carbon. So you have 1, 2, 3, 4. You have 5 carbon-hydrogen bonds. You have 1 carbon-carbon bond. You have 1 carbon-oxygen bond. And you have 1 oxygen-hydrogen bond. So you have 4 different types of bonds. And this one you have 5 of them. And the rest you only have 1 of each. Now what use is that? Well, in order to break those bonds, these are all endothermic reactions. You have to add energy to each one to break it. But if we do that, then they can rearrange themselves. And when they come back together, they're going to give up some energy. Or you could say something like this. We're going to burn that ethanol in our sterno pot, right? To keep our food warm. So you're burning ethanol with oxygen, and it gives you carbon dioxide and water. Okay? So that's not balanced. But it's just to illustrate the different types of bonds. Right, that's a bonus. So if you know the bond energy, that the energy that is given back to you when this bond forms, when that bond forms, when that one forms, and that one forms, and the amount of energy you had to put in to break those bonds in the first place, then you can add those together, because we want to be negative and want to be positive, and you should get a value that's equal to the enthalpy of that reaction, simply by budgeting all of the bonds in your balanced equation. And there's your list. This is not a complete list, but it's useful. So each one of these bond types has associated with it an energy. And then if you take those energies and you say, how much energy is required to break the bonds? Then you subtract the energy that is for the formation of the bonds. And all of these bond energies are positive. Right? Even though we're saying they're exothermic and endothermic, the bond energies are listed as positive values, so that when they go into this formula, the negative turns this energy released into an exothermic value. Right? So all the positives together with this negative means that these are endothermic and exothermic, excuse me, because they're negative, and these are endothermic. So that's why it's in this order. Those total minus these total gives you the enthalpy. So here's an example. Yeah, I've got about 3 minutes. So here we have this compound and that compound. And notice the only difference here is that on this side, carbon is bound to nitrogen. On this side, carbon is bound to carbon. But this one has 3 carbon-hydrogen bonds, and this has 3 carbon-hydrogen bonds, so there's no change there. And this one is a triple bond between nitrogen and carbon. And this one is a triple bond between nitrogen and carbon. Right? So there's really no change there. The only change that you have to consider is nitrogen-carbon versus carbon-carbon. Nitrogen-carbon versus carbon-carbon. Because the rest of them are equal. So if we say this one, nitrogen-carbon is 305, we got one of them, and then we subtract carbon-carbon, 347, right? Then what do you get? Let's see, that's 2, that's 4, right? So negative 42 kilojoules per mole. So that should be the enthalpy of this reaction. Okay. We could have gone through and added up all of these other bonds and all these other bonds, put those in there, but they'd all cancel one another out. So these are the only 2 that changed in that process. That's not always the case, right? But in this case, it simplified our whole process. We're recognizing that which ones changed and which one didn't. Okay, this might be a good place to stop and pick this up Monday with a localized electron model. So what's today, the 10th? 11, 12, 13, 14, 15. So we'll pick it up on the 15th. That's a bonus day, so we're good. We can finish this on Monday, and then we'll have Wednesday to review, and then the following Monday should be exam. Yeah, the 22nd. We'll be here next week. Okay? So now we're going to go in the lab. That's the fun. Signing off.